Okay, so the plan of attack today is I'll do a quick review of last class, and then hopefully answer the question about pressure. And then we'll describe the different types of energy, and then define mechanical energy.
Power. Are we doing that today? No, we're not doing that today. We will. Yeah. For the objectives? Yep. Okay, so forms of energy. You already know them, but it's good to review. Kinetic energy. So what's kinetic energy equation? Did you get those, Ben?
Yep.
Okay. Yeah, 1/2 mv squared. And m is your mass, and v is your velocity. Now, you will see this a lot. Little ke, what do you think that is? Specific kinetic energy. And actually, this equation is 1/2 v squared. Because what's the unit now? Could be joules or kilojoules per kilogram. Yep. You will see that. Okay, potential. I think we're going to cover, my guess, when is it going to be? Friday will be the first law. Basic fundamentals of the first law. So potential energy, remember that equation? mg h or z, doesn't matter, yep. This is your mass, g is your acceleration due to gravity, and this is elevation.
Anytime you do potential energy, you should have a datum.
Right? What is a datum? The reference point. If you're above your datum, your potential energy is positive. If you're below your datum, potential energy is negative. What's that?
It is just dependent on if the system is doing the work. We'll talk about that next week. Okay, you'll see negative and positive and what the difference is. Okay, because there's equations that I want to show you that do that. Okay.
What about little pe? What's that? Yep. So it'd be just g z. Okay, the last one, actually there is one more, but we won't cover that till probably Wednesday. Oh no, we will cover that. Okay. We have internal energy. Yep. Yep. Internal energy.
There's no real equation for this until we get later on in the semester, but you'll see internal energy as big U or little u.
And all internal energy is it's just dependent on temperature. So if you're at a certain temperature, or the fluid or the gas or whatever's at a certain temperature, it has a certain internal energy. Okay, and you can kind of think about it as how fast the molecules are moving. It has so much energy. Okay. Total energy, you just add them up. And there's other energies like magnetic, electrical, and chemical, but we're not going to include those right now. You may also see the change in energy. So that's just the change of kinetic potential and internal from two different points. Questions so far? All right, some other information that we need to remember or define if you haven't taken this. So let's look at flow definitions. So mass flow rate. What's the basic definition of mass flow rate? It's m dot, meaning it's kilograms per second. So in differential form, that's the change in mass over the change in time. Anybody remember the other equation we can use if we know the velocity and the area? Rho A V. Yep. So the density of the fluid times the area, cross-sectional area, times the velocity will give you mass flow rate. Why? Well, check the units. Kilograms per watt. Meter cubed times meter second times meters per second. What does that give you? Holy smokes. Kilograms per second. That's cool, huh? So rho is the fluid density, A is your cross-sectional area, and V is your velocity. How about volume flow rate? Oh, didn't mean to do that. Volume flow rate is your cross-sectional area times your velocity. So how can we rewrite m dot as? Yep. Rho times volume flow rate. So just as a side note, sometimes it's written like that. You could also have energy flow rate. Anybody want to guess what that symbol is? E dot, and then it's m dot times little e. What's the unit of little e? It's just specific energy, right? Kilojoules per kilogram. Because what's the unit of m dot? Kilograms per second. So you have a joule per second. Okay, so let's talk about mechanical energy. So mechanical energy over here, defined as the form of energy that can be converted to mechanical completely by an ideal mechanical device. So this is really, make sure you put this up here, it's a fluid energy. The students that have taken thermal, think of Bernoulli's, all right? I know, but, wait, what did I say? Oh, so taking fluids, thank you, okay. I had that completely different in my head, apparently. Bernoulli's equation is really this, okay? So mechanical energy is really energy of the fluid, okay? So if you take your gas pump, all right, go to the gas station and you fill up. When you hit the button, it takes the energy from that tank and moves that fluid to your gas tank. Okay, so you're looking at basically a liquid or a gas. Most of the time, it's easier to look at a liquid, like water, like a pump. Okay, so we're going to look at the energy of that liquid or of that gas. So it's basically saying that there's no heat transfer in mechanical energy. We neglect heat. We just look at the mechanical part. Okay, so we're going to do an example, and I'm going to show you a little bit more on this. Okay. Most of the time we look at turbines or pumps for this. Yep, that's a turbine. Yep. 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 All right, so one thing before I show you this setup here is for fluid energy, we have to include what they call flow work. And there's no symbol used for it. They just call it flow work. Yes, right here. Yep, and that's specific volume. Yep. So again, mechanical energy is only looking at the energy of the fluid. So that's the biggest thing to remember. So let's take an air compressor. We pump it up. It's got a high pressure inside, right? And it's sealed. That has energy. That's what this is. It has like some sort of pressure energy. When we open the valve, all that pressure is basically being applied and pushing that out. Okay? So that's converted to kinetic. Does that make sense? That pressure energy is then converted to kinetic. Now, if, in the example I'm going to show you, if we have water like a dam and it falls down, you have pressure and you have all this other stuff, okay? So let's look at this, and I think this is very similar to the practice problem I'll do.
That's P over rho.
P over rho, yep. So here is, let's look at this. It's like a dam, and there's like a turbine right here, and the water's flowing through it. So we're going to pick 2 points. liquid, water, has energy, right? So it has this mechanical energy. We're going to neglect heat, so it's mechanical energy. And I picked two states, one on the top left and one on the top right. Could I pick my point 2? Could I pick point 2 like right here or right here? I mean, you can. It's fine. Sure. Right? Because we're looking at energy. We're looking at what's happening to, it doesn't matter. Energy is conserved no matter where you are. Okay? In a direction of flow. At state 1 and 2, what can we assume about the level of the water and the velocity? In this case. If it was like a stagnant and it's just pretty high, these velocities could be 0. Right? Okay. But if we pick point 2 here, is point 2, does that have a velocity? Yeah. Okay, that's fine. Doesn't matter. Okay, what about the pressures? What is the surface touching? Atmospheric. So they're both atmospheric, right? Yep. Okay. But what's the main difference? Elevation. So it has potential. Okay. But let's write the general form for all this, which will help you in the homework in this next practice problem. At state 1, it has kinetic, it could, potential, and flow work. So let's put them in units of kilograms. So V1 squared, 2, plus GZ1 plus P1 over rho. At state 2, it could have kinetic, could have potential, it could have flow work. V2 squared over 2 plus GZ2 plus P2 over rho. Now we're looking at the mechanical energy, and we're looking at the change in mechanical energy, so what do we do to find that? Just take state 2 and subtract state 1. So let me write this fully out. And the reason I'm doing this is because this is what I want you to start doing on your homework. Write the whole equations out that you have, and then cancel everything. Yes. Oh, did I switch that? I'm sorry. This should be V2 on the beginning here. Yep. Is that what you meant? Yes. Yes. Sorry. Thank you. Is that what you were talking about, Ben? Yep. Sorry, I didn't catch that. So in order to find the power, which is the change in mechanical energy per unit of time, which we also define it as a W dot as power, then it's just your mass flow rate times your change in mechanical energy. So basically here we had a dam, and the elevations, we picked 2 points. There's no velocity at either point. The pressures are the same, so you just have a gravitation. So if we know the mass flow rate going through that turbine, then the maximum potential energy or power we could possibly get is the change in potential times your mass flow rate. That's what this practice problem I'm going to do. And I had it printed out and I forgot to grab it, but that's fine. I'll let you write it down. It's not too long. Questions? Questions so far? Make sense? So it's really Bernoulli's, it's just fluid energy. So let's do this practice problem. A river flowing steadily at a rate of 175 meters cubed per second is considered for a hydroelectric power generation. It is determined that a dam can be built to collect water and release it from an elevation difference of 80 meters to generate power. Determine how much power can be generated from this river water after the dam is filled. While you're doing that, I'll just set up the problem. What's the density of water? 1, what's the unit? 1 gram per cc, or it's 1,000 kilograms per meter cubed. So remember that. So it's kind of looking for, these are generic kind of general questions. We'll be more specific, but basically it's looking for what is the maximum power that can be actually generated if it fell, was it 80 meters? So the sketch is very similar to what we had. So I'll just kind of draw it real quick. I know you can't see it yet. Okay, let's see how this, everyone have this? Can I go back to the, so you would start doing this in the problem, right? You're given through your sketch, okay? So go ahead and write that down, then I'm gonna just tweak a little thing, a few things. And let's pick our points here and here. And I'm going to try it. Hopefully it works. Oh. So what I tweaked was I labeled Z2 down. So this distance you can call Z2, 80 meters, where my datum was at 0.1. And we're trying to find the power. So as you're finishing writing this, what do you think the assumptions are that we could use? Yeah. Yes, you could do that in the givens, sure. Yep. 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 I was going to talk about that when we get to the solution, but that's fine. Yep, because it's down, it's below the datum. So before we do the assumptions, let's talk about that. So what happens to that energy as it falls through? It converts to kinetic, but our point 2 is over to the side, so we're not assuming velocity. But when you drop something, the potential energy decreases, right? Which becomes negative. Where if I raise this block up in altitude, it's above a datum, that means I'm gaining energy, okay? So that's the difference between like a positive and negative. So let's go back to the assumptions. First assumption would be that water is incompressible. That's always the case right now. And the other one is we're neglecting any heat, right, between these systems. Any heat that's being generated to raise the temperature or anything. So that's why it's like a mechanical energy. We're only looking at that part. Okay, so let's get to the solution. I'll do it right here, but just to save some space. So we know that the change in mechanical is m dot times a little change in mechanical, right? Is that what we had? I hope so. Yes. So I should have a heading. So find power. So let's find the mass flow rate. What's given in the problem? Density and volumetric flow rate, right? So how do we find mass flow rate? Yep. So m dot equals 1,000 kilograms per meter cubed times 175 meters cubed per second. This is 175,000 kilograms per second. All right, let's find change in mechanical. And we have that. So let's write that fully out. Oh, that was V2 squared over 2 minus GZ2. No, plus, right? Sorry. And then just make sure I have it right. This is the pressure. Let me fix that. So if we pick point 1 and 2 way away from where the velocities are changing, the velocities are neglected. And what is the pressures at those two surfaces?
Why is it
The same, yes, because we picked the points, so they're far away from these. They're like the top of the surfaces, so we're going to assume that they're really close to 0. Okay? So these are just trying to find like a maximum case, okay? The pressures are the same, they're atmospheric. So now we have what? Yep, and Z1 was 0. So the change in mechanical is just GZ2. So we can find that. The negative sign just indicates kind of like we're losing potential, or so don't worry about the signs. The signs are fine because we're trying to find like a maximum case. Did I do that? Oh, why did I put G in there? Yeah, that's where our datum is. Yep. Yep. I got 0.785 kilojoules per kilogram. Negative. That's fine. The negative is just there to tell you where it doesn't really matter because we're looking at two different states. So don't worry too much about the negative because we'll find out this is just a maximum case. And now, what do we have? The power is 175,000 times negative 0.85. Oh, we get 137 megawatts. We could put the negative in here, that's fine. But it's just, again, based on our location of datum. We could have picked datum at 2, right? If we did that, then what would Z1 be? It would have been 80, and this would have been positive. So it depends on your datum. That's fine. It doesn't matter. Okay? Just like forces, if you calculate your free body diagram, you get a negative force. You just know, okay, it's going in that direction or negative, whatever, okay? So it's just a direction, so don't worry. So this actually is the maximum possible case you can get with this water flowing through here, changing 80 meters down, okay? That's the maximum energy you can get. It's definitely going to be lower than this, right? For sure. But this is a good guess. Questions? What is a joule per second? You remember what a joule is? It's a Newton meter over a second. That's what the whole watt is. So inside there is the kilograms inside the Newton. Okay? Because well, I didn't actually put the units in, but let's do the units. What was the units of 175? So kilojoules per second times, we'll just do joule per kilogram. So you get a joule per second, which is really a watt.